Let us go to the topic, to the main topics of this, the lecture of today, which is the Supremum. Okay, so let me just write what is infinity. It is just a symbol, nothing more. So the chapter here is the notion of Supremum and the notion of Infimum. So, as I told you, the reason of introducing Supremum and Infimum is that the more natural notions of maximum and minimum are not so complete, not so flexible. There are many sets in which you don't have either maximum or minimum or both. So the first notion is the notion of upper bound. We start from the notion of upper bound. So the definition is the following. Let A be a subset of R. Okay, then every number k element of R such that all elements of A are less than or equal to k, so every number k that it is rightwards in the line with respect to the whole set A is called an upper bound of A. In some texts you can also find the word majorant, but in general upper bound is better, is more common. So this means the following. Consider the line, the real line. Okay, this is the real line R. Then you have your set A, which is made of some intervals, for instance, some points, some dots here and there. And so this is, the blue set is A, and for instance, the point here, which is on the right hand side with respect to the whole A, this is K, this is, sorry, this is called an upper bound of A. Okay? Of course, there can be sets, subsets of R that have no upper bound. For instance, R plus or R itself have no upper bound. So, another definition, this is just a name. If a set A, subset of R, has at least an upper bound, then it is called upper bounded. Okay, this is a very natural, very simple definition. And now the next step is to consider the set of the upper bounds of a given set. So let me copy the picture here. We have the set A. So notice that K here has been introduced here in this picture as an upper bound of A, but notice also that there are many other upper bounds. Of course, all numbers larger than K, and also numbers here in the space between A and K. So the upper bound here form a half line, a right half line. And what I'm going to prove now is that this half line of the upper bound is a closed. So to say, it admits a minimum. Okay, this is a theorem, this is a true theorem. And it is quite a deep theorem, as you will see easily by the proof. So the theorem says let A be an upper bounded subset of R. Okay, then there exists the minimum of the set of the upper bounds of A, namely there exists M in R such that this capital M is the minimum among all k's in R that are upper bounds of A. Okay, it is exactly what I told you before, is that the half line of the upper bounds is closed. And the point here is, of course, the minimum of the upper bounds. So, I give you the proof of this theorem, which is very interesting. So I like to give you this proof in a complete way. First of all, let me fix the notation. So let us introduce the notation, which is nothing, just a symbol for the set of all upper bounds. So this is up of A is equal to all k's in R such that k is an upper bound of A and okay, let me just stress what is an upper bound. So by the very definition of upper bound, one immediately has that for every x in A, for every k in up of A, one has x is not larger than k. So let me represent this situation pictorially. So this is the line of the reals, and here you have the set A, for instance, in red, and here you have the upper bounds that are here. So notice here you have two sets. One of these sets, so the set A, is completely on the left-hand side of upper bound of A. So there are two sets, one on the left of the others. And now we use Dedekind axiom, so the notion of completeness of the reals. Which is exactly the axiom on which I insisted too much in last lecture, that says when this is the situation, then there is a separator here. So there exists an element psi in R such that for every choice of x in A and every choice of k among the upper bounds of A, one has x less or equal psi less or equal k. Now, this psi here exists. Notice that since this part of the double inequality holds, x less or equal psi, we have that psi is an upper bound of x, sorry, of A. So we have that psi belongs to the upper bounds of A. Moreover, because of this part, we have that psi is not larger than any upper bound of A. And since it is an upper bound of A, we have that psi is the minimum of the set of the upper bounds of A. So this minimum exists. And I want to highlight again, I want to point out that it exists only due to the Dedekind axiom. Okay? So, then, setting M equal to psi, the proof is complete. Okay? And this is the basic step in order to introduce the supremum. So the next definition is to supremum of an upper bounded set. So let A be an upper bounded set an upper bounded subset of R. Then the minimum of the upper bounds of A the minimum of the upper bounds of A means so it's something that exists. We just proved it. So this minimum of the upper bounds of A is called the supremum of A. And is denoted by symbol one uses is sup A. Okay, let me clarify all notions we introduced by some examples. I want to retain the same examples as before and as when I introduced the maximum. So the first example is given by the interval, the closed interval 0, 1. Okay, we already showed that the maximum of A is equal to 1. A is upper bounded. For instance, 2 is an upper bound. And I want to be perhaps too slow and too pedantic, but I want to be clear. So here we have 0, here we have 1, and the interval we are interested in is this. 0 here, 1 here, and so here is the half line of the upper bounds. This is up of A, and this is A. So what is the minimum of up A? Let me understand what is up A. Up A starts from 1 and goes to plus infinity. But notice that 1 is not only the maximum, but it is an upper bound of A. Because all elements of A are not larger than 1. Moreover, any other upper bound of A cannot be less than 1. Because otherwise 1 is larger than that mysterious upper bound of A, and since one element of A is larger than it, it cannot be the upper bound. A very simple way of reasoning. Okay, nothing special, really nothing special. So the conclusion is that 1 is the minimum among all upper bounds of A, so 1 is the supremum of A. Notice that here the supremum equals the maximum. This is not by chance, this is a rule, an easy result to prove, an easy result to prove. So I suggest you to try to prove it, and the result is the following. If a subset of R, A, has a maximum, then the maximum is the supremum too. Okay. And as a homework, I suggest you to prove it. So I want to stress here what is the set of upper bounds of A. Here we have that set of upper bounds of A. Here is 1 plus infinity, and 1 is included. Okay. So let us go to the second example. Again, it is stolen by the last example we did. We have A equal to 0 closed, 1 open. And of course we already proved that it has no maximum. Again, the situation is like before. I copy here the picture, sorry. The only correction I have to bring to this picture is the fact that 1 is not included here. So let me cancel it and let me do it like that. But the set of the upper bounds is again the half-line 1 plus infinity, and of course 1 is included. 1 is included because 1 is an upper bound for the interval 0, 1 open on the right. I want to stress this fact here. This is the set of the upper bounds of A. Go to the last example and the set of the upper bounds of A was exactly the same. So the set of the upper bounds in these examples is insensitive to the fact whether the extremes are included or not. And this is why the supremum is a good notion, is an elastic notion, is flexible, because it is always present here in the set of the upper bounds. And so again we have that 1 is the minimum among the upper bounds of A, and by definition of supremum, this is the supremum of A. That's really good. So, I can give you some exercise too and try to prove these facts. First, consider A as the set of the numbers x divided by x minus 1 for x real number minus 1. Establish whether it is upper bounded. And if so, compute the upper bound. And the other example is A is equal to the set n plus 2 divided by n plus 1. This time n has to be caught in the set of naturals. And the question is the same. Is established whether it is upper bounded or not. If so, compute the upper bound. And of course, symmetric to the notion of upper bound, there is the notion of lower bound. Okay? And the construction is the same. Sorry, it does not compute the upper bound, compute the supremum. And now we introduce the notion of infimum. So the first definition is the following. A subset A of R is said to be lower bounded if there exists a number L in R such that for every x in A, L is on the left-hand side, the real line with respect to x. And again, the picture is very simple once you get the notion. And here you have your set A. This is A. And here you have L. And L is said to be a lower bound of the set A. And another definition is that a set, we say that law of A is the set of the lower bounds of A. So it is the set of L in R such that L is a lower bound of A. Now the theorem is the following. Of course, if it's completely symmetric to the theorem we proved for the supremum, for introducing the supremum. So we have that if A in R is lower bounded, then the set low of A has a maximum. The proof is left for homework because it is really analogous to the other proof, the proof of up of A has a minimum. And the definition that follows is immediate. So we say let A be a lower bounded set of R, then the infimum of A is nothing but the maximum of the lower bounds of A. So the definition is that infimum of A is maximum of low of A. Okay, to complete everything, we say that there is a convention that says if A is not A subset of R is not upper bounded, then the sup of A is said to be plus infinity, and if it is not lower bounded, the infimum of A is minus infinity. Okay? As a remark, I stress that for every A which is not empty, the infimum of A is not larger than the supremum of A. I say not empty because for the empty set there are strange rules. I don't want to talk to you about that because it is strange and it is completely useless to our purposes. And as a homework, I ask you to find a set, a subset of R, such that the infimum is equal to the supremum. The last definition is the following for this part. Then we will move. The definition says that if a set, subset of R, is both simultaneously lower and upper bounded, then it is said to be bounded. Namely, it means that there exist L and K, real numbers, such that for every x in A, x lies between L and K. Okay, this is the picture. You have the real line here, and here you have your red set A, as usual, and here you have lower bound L and upper bound K. Okay, this is equivalent to saying that this is completely equivalent to saying that there exists M in R such that for every x in A, we have that x is less than the absolute value of M. Of course, I still did not introduce the absolute value, but I know you know what is the absolute value, and so I will introduce later. Okay, and this new definition amounts to nothing but having your red set A here, and you consider as a reference the point 0, for instance here, and then you can take here minus M and here plus M. The idea of being bounded is that it can be contained in a box. Okay, this is the notion here in the first definition. The second definition, you just say that the box can be centered at the origin, even though the set you're interested in are strongly asymmetric with respect to the origin. But this is not important. You don't ask this bound to be optimal, just to exist. So sometimes, for a reason of writing and or explaining, it can be shorter and then more comfortable to use the second notion. Don't be scared if you meet it. Okay, end of the second part.